Good morning, this is David Cuartillas transmitting live the Arduino LiveCast number 14. Sorry, I'm just waking up. It's 8 a.m. so I'm making an experiment trying to transmit any time in the day. As I said, during this week, it's a European Maker Week 2018. I'm going to transmit once a day or sometimes even twice a day different contents that have to do with the maker culture and obviously related to Arduino. I'm having a project that I'm doing over the course of probably it's going to be more than 1 week as I see it right now, that consists in hacking together a shield that you can see here. It's a shield, it's called the AudioHacker shield, and it's meant to be doing meant to be allowing you to do experiments with sound. It has a digital to analog converter, an analog to digital converter, some RAM memory, and an amplifier, so it's possible to take sound, filter it digitally and push it out again to, for example, make a guitar pedal or sound looper or some other things. And I am experimenting with it, and the things that I did, I first soldered it, then I tried the libraries. I didn't get what I wanted, but I wasn't understanding what I was getting, so I started analyzing each one of the components one by one, trying to see how they work and work with the software. So on the one hand, I'm going to be doing that project during this week and probably will expand to next week. I'm also going to be transmitting content from a robotic competition in Spain called RoboCampeones, and that will be tomorrow, Thursday. Unfortunately, I got told that the internet connection at the place I'm going to be visiting is not so great, which means that I will record the livecast as if it was live, interviewing people there, like some teachers that are organizing the event and some students that are building robots with Arduino, and I will transmit it live as soon as I get a proper internet connection and attend the chat. I will also try to make a program from Makespace Madrid, which is the first community supported or community created Makespace, and I'm not really sure, but I think it's one of the first in Spain. And I will as well transmit something from an educational conference on Friday and potentially even on Saturday. So I'm trying to really have programs every day in the week this week, which have to do with maker culture one way or the other. And in parallel, I'm trying to learn something. This is a bit just for me, but also since it's taking a component that is made by somebody in the Arduino community, trying to learn the thinking behind this project and see how it works and see if I can do anything out of it for myself. So as I said, just recapping with the things I've been doing until now. I just took some notes yesterday that I want to share with you in case you weren't with me, or in case you just need to recap before we continue working with this today. This shield here is meant to be taking analog sound, digitizing it, and giving you the opportunity to try it out. For those of you that don't know anything about digital sound, analog sound typically electrically is working between 0 and 5 volts, and 0 is at the bottom, so the signal is going from like 0 volts to 5 volts, something like this, and it's oscillating. So if you, for example, have a sinusoidal wave, which will be a pure tone, it will oscillate like this, and it will be constrained between 0 and 5 volts. Digital technology can't work with signals that are continuous in time, so what we do is that we sample this in time, and the shield we have here allows us to have a pretty high sample rate, up to the same speed as the CD, but the default sample rate is 22,050, which is half the CD speed. Then it also quantifies in amplitude, and it has a 12 bits quantification, which means that the values go between 0 and 40 4095. And this is a bit different from when you use analog read in Arduino, because analog read in Arduino, as you know, is working with 10 bits, which means that the maximum value you're gonna get is 1023. Okay, so it's important to note this, because it means that we have a lot higher resolution in sound, which give us a lot better sound quality. So you can do very compelling sound devices if you have 12 bits resolution. Then the shield itself has 5 chips. 4 of them are digital and 1 is an analog amplifier. And the digital ones are 2 RAM chips, 1 digital to analog converter, and 1 analog to digital converter. All of them work over SPI. And those of you that don't know what SPI is nothing but a serial port that is a synchronous serial port. It's not like the serial port that we use to communicate to Arduino, which is asynchronous, which doesn't have a timer. It does have an internal timer, but the devices need to synchronize themselves externally. But SPI has a master in the communication that is sending a synchronization pulse in a separate pin, which keeps allows you to reach much faster speeds. So there is a bunch of pins on the Arduino Uno board that are going to be used to generate this. So it's like a clock pin. There is a signal out from the board. There's a signal in, and there is a chip select. And that chip select allows you to have multiple different chips that are reading stuff. So typically, the application will be something like I'm gonna finish with this explanation, and then I will make another drawing explaining how this works conceptually. Then there is a timer that is used to synchronize all of these readings, and we're using timer 1. And since we're using timer 1, what we're doing is that we're generating a timer that at a certain frequency, which is actually the board's clock divided by 4, which is 4 megahertz. And every time this event is triggered, then we can do operations with the library, which are reading the ADC, writing to the DAC, writing to the memory, and so on. So this means, this is something I realized yesterday, that I don't write my code in the loop. I can write things in the loop, obviously, but where I write my code is inside a timer, an interrupt servicing handler. And it also means that if I run code in there, some traditional Arduino code will not work. Like, for example, writing the delay, because delay is using interrupts, and inside an interrupt handling function, you cannot really trigger other interrupts. Which means that if I want to make a delay, which is not good practice, but I just made it yesterday for the sake of simplicity and showing things on the screen, I need to use delay microseconds, which is a function that does not work with interrupts. So this is very important, because we're learning a lot of different things. And as I said from the beginning, this is not really meant to be a LiveCast for newbies, but if you are, I'm going to be making my best to explain things very, very easily so that you can learn stuff. But sometimes I will have to bring out knowledge that I have that is not exactly easy to understand, because for example, just knowing some of these things requires reading the 390 pages of the manual of the chip on the Arduino Uno, which is the ATmega328. So I wanted to try to make these things as easy and digestible as possible. So then the question is, how does this thing here work? And again, I'm working under a lot of I'm imagining how many things work. I'm just exploring this, because sometimes people say like, oh, how can you know this? How can you do that? And what I'm trying to highlight is that many times when working with technology, what we do is that we have some knowledge, and then we just try to apply it and learn some stuff as we go. And this is what I'm doing with this experiment. I am trying things out slowly, and it's not that I know everything about the shield. Actually, I know very little about it. So I'm just trying to learn about it from a bit of a holistic perspective. I'm looking at it from the outside, and I'm trying to apply the knowledge that I have, and then I check whether it works as I expect it to work, which is a very nice way of, I think, exploring technology. So let me just get my black pen, and let's take a look at how this could work. So you will have your ADC, so you will take a signal from the world, so there's a sound signal here, and we measure it. Most likely there's an amplifier before this, but for the sake of simplicity we're going to do it like this. And then there is the chip on the Arduino, which is the CPU, and this will trigger the ADC and tell it to read some data. And then I'm gonna draw in purple the data flows. So there will be a data comes out from the ADC, and this data can be read into the CPU. And so ideally the way I would do this would be having the RAM chips hanging out here. There is two RAM chips, RAM 0 and RAM 1, and have them connected to the same data bits, and have the CPU have the pins that control the activation of each one of the chips, and finally have the DAC out here. And again, so a situation like this allows for reading data, put it into the CPU, process the data, and then either send it to the memory to store it and eventually read it later and process it again, or send it to the DAC so we can hear it. So this is, in my opinion, how this is going to work. There is a final chip that goes here, which is a sound amplifier. And here we will get a different version of the sound. For example, we do a robotic voice converter. So if I want to make operations with the sound, I need to, in sampling time, read some data, process the data, and eventually send it out, or read the data, store it if I want to make an echo, for example, and then read the previous data, take it out, add it to the current data, and push it out to the DAC. So you see, making sound algorithms requires keeping this in mind at all times. And if you look at the code, like we saw the echo yesterday, it's doing some of these operations. Then it's using some low-level functions here and there, what doesn't make very easy to understand how it's working. And I think it's because Michael, the maker of the shield, he's actually pretty good at this, and he wrote some code that works. It's not necessarily super explanatory, but we're gonna see if we can learn about how this works properly to then eventually use it later. Let me adjust the camera a little bit, just like this. Okay, so where to continue? So yesterday I checked out the DAC, and in order to check things out here, again, just to recap, I'm trying to make this thing as if I was a person that only had one Arduino board, which is not true. I have a couple of hundreds in a box out here in my shed, but let's say that I'm trying to test this out. Let's say I'm a student and I bought the Arduino board, and I bought this thing because I'm gonna make a project, and I'm trying to troubleshoot it. Which techniques can I use to troubleshoot what I'm doing with just one Arduino board? So this is kind of like my dogma at this point. I'm also trying not to use external tools like a multimeter or an oscilloscope, which, by the way, at some point I will have to use. Probably next week when I go more in depth with the shield, just to check out that all the signals look nicely. I will end up using an oscilloscope just to also show it to you on the LiveCast. So the question here is, how can I test the DAC, which is what I did yesterday. So I thought, okay, what if I take my Arduino and just say Arduino tells DAC to write a voltage. And for those of you that don't know what a DAC is, it takes a digital number within a range and transforms it into a voltage. So for example, if the range is 12 bits, let's say we send the number 2000 more or less. 2000 is more or less half of 4095. So the voltage out will be around 2.5 volts. Okay, that's very clear. So then, second, Arduino reads on analog pin connected to DAC output. So in this way, I can then write something to the DAC and then use a CPU with a different wire, and I'm gonna use a different color, and I can measure what's going on out here, or eventually out here, you know, either at the outside of the output of the amplifier or at the output of the DAC, and I can read that value inside Arduino and check it out. So, and then to be even more relevant, I could be doing a program that is changing the value, and I keep on reading. Change out on the AC and repeat number 2. Okay, so this strategy will allow me to then check constantly what I'm doing, and this is what I did yesterday. And what I did yesterday translates into this. Here you can see this. What is it translates into this, and this is the reading. And right now it's stopped because my board has been off, but I just need to restart the serial port and see if it works again. No, it doesn't find the port because I need to disconnect and reconnect. I left this whole thing running through the night, and probably I provoked even a short circuit in the board, yeah, because the wires were hanging loose. Okay, so let's see if the port is there now. Yeah, there is the port, and I open the serial port, and here you go. So this is what we did yesterday. So yesterday we wrote to the DAC, and we read the value, and we wrote using a for loop, and this you can see in the code. So this is how far I went until now, and this basically proves that the DAC works. So if theoretically, if I run examples written by Michael from Nootropic Design, I should be able of at least trust that the DAC is gonna work. So the question is, does the ADC work? So that's the next thing I need to test. I need to test that all of the small parts in the system work properly, just to make sure that my system is working. And if right now I'm looking at the function, at the code that I wrote the first day, and if you remember, there is part of the code that is for reading, and I also made some code that was, sorry, for writing the ADC, and I also made some code that was meant to be reading the ADC and printing out the value. So I will then transform this function that, as you see, does not include the interrupt handler, and this does not include that the delay should be made differently, because once it's inside the interrupt handler, it's not going to work. So I will copy this, or even better, I will just make it this way. So we'll have a single interrupt handler, and I'm gonna just have 2 different types of executions, and one execution is gonna be run the reader, and the other one is gonna be do the writing step. So no, it will be write test, and on the other hand will be if read test. No, I will do it else, because this is going to be one or the other. Else, like this. And then I can delete the whole declaration of the loop, like that. And then I can have the delay to operate for both of them at the same time. And I will comment this, make a delay. So what this is doing now is that if I'm doing a write test, I will write and I will read the analog port and print out the value. If not, I will basically read the ADC, and that will require me to be fiddling around with the cables and changing the voltages and print out the value that I'm reading through the ADC. Okay, read ADC is reading a value that goes between 0 and 4095, and I will check that this works fine. And so I need to declare either a variable or a constant that is called write test. So I will just define write test, and I will make it 0 or 1, 0. Because if I make it 0, I'm not doing the write test, I will be doing the reading test, which is this one here. If I make it 1, I will be doing the test I'm doing right now. So I can just send this to the Arduino board, and we're gonna see whether the ADC is giving us any value. Oh, I have the delay 100, but as you know, delay 100 is not gonna be doing anything. I can delete it. So right now, if I'm reading without any signal on it, the voltage or the value I'm getting is about 2040 something, which is half of the reading of the ADC. And funny enough, this is the same value I was getting the other day. But if I'm getting this value, it means that, in my opinion, the ADC is working, because I must be sending a command to a digital chip, which is the ADC chip, and it's having nothing at the input, and it's reporting that the value at the input is 0. As I said earlier, the digitalization of the signal requires that half the voltage, 2.5, will be like the average input. Sorry, will be the 0 input. So the 0 input, 2.5 volts, is translated into half the digital reading, which is 2000 something, which is half of 4000 something. Okay. So what happens if I change the voltage? So what I'm gonna do next is I'm gonna just change the wires here, and I'm gonna affect the input and try to put 5 volts at the input of the chip. So I will change this one from there to there, and I will just use the green wire that's going to do 5 volts to see if it affects the reading on the input, and it clearly doesn't. So I'm theoretically right now pushing 5 volts into the board, and it should be changing the reading at the input. So what is happening here? Well, I'm having this kind of like an idea of what's happening, but first of all, before I tell you my theory, we know that there's a potentiometer here that is the gain of the amplifier. So I'm going to try to change the gain of the amplifier to see if that affects. So I'm changing the gain of the amplifier, and there is a small change in the reading, but nothing that's insignificant. It looks like more like the amount of noise is changing. So two things might be happening here. Either the ADC, which is the chip up here, is broken, or and it's only throwing me the 0 value, or there is something that I've missed in how to configure the reader. According to the reading I made of the library yesterday, in principle I'm not doing anything wrong, but I will dive into the library now. Or what also might happen is that since this signal has to be decoupled. It has to be removed from its own continuous component. There must be a capacitor at the input that's eliminating continuous current, and if I put basically blank 5 volts, this will not be giving me any signal at all. So so that is not really good. So let's try again, just to confirm. I made a short circuit, I think, because I blocked the serial port, so I will make sure that it's connected and open the serial port again. There it is, yeah. Yeah. So you see the values, they keep on oscillating. And when I apply voltages to them, oh, now there is a difference. Or, oh, look at this, now there is a difference. I changed the bypass switch, and now when I don't apply anything, I get 2000 something. And once I apply the voltage, it goes up to 2100 something. So now we start to see something. So it looks like the ADC is also working. This is really good. And the fact that there is a slow change is because of my software doing the slow change, forcing the thing to be delayed. So okay, it looks like ADC is working. So we confirmed then that both ADC and DAC are working in the system. So this is really good news. We have 50% of the thing working. So if ADC is working and if DAC is working, I could write my first system that will just bypass the signal. Will just take the input and then send it to the output. So that could be a thing, just to test it out. So this is the way I'm going to be writing my code is going to be one that will allow me to have all of my code in a single place, just to make it very easy to refer to it. So I'm going to change the structure of how I'm writing things here. I'm going to use a switch case to have multiple different cases to be writing things, and then I will be calling small different functions from here. Again, this is not super good practice when dealing with interrupt handlers, but it's just to write the code in a very clean way, so that if you wanted to replicate my experiments, you could do it easily and understand how things are structured. And this is the way I would typically write things. I will make small state machines just to make it simple. So instead of, I'm going to define different kinds of things. I will have the write test. I will have the read test. And it needs to have a different number. I will have bypass. And this is a bypass by a software because there exists a bypass already by a switch. Okay. And I will add more things later. And then here I will have a switch case, switch mode. And which means I need to define a variable called mode that will be taking the value write test, read test, bypass, or whatever other states we defined later. And I will make it volatile because it's going to be running inside. It's going to be running inside the interrupt handler. So when you define variables that will be running inside the interrupt handler, you should typically define them as volatiles, and then the type. I forgot to write the type like this. And by default, I will write here the one that I'm interested in. So I did the write test and read test already, so I'm going to just try out bypass, which does not exist yet. And then inside the loop, I just need to do case write test, break, case read test, break, case bypass, break. and then here I can copy the code and put it in. I need to have the delay inside there. I will just clean the mess later on. I'm just like making sure I have everything that is needed, and I make the delay. Okay, so here you see, if the mode is write test, then I do this. If it's read test, then I do that. If it's bypass, I will read the input, which will be this one, and then I will just write it to the ADC. And I will not make any delays in case I am doing this operation like this. Okay, so this is gonna probably throw an error because of the way it's defining variables, but I just want to check it out. So this is a very clean way of doing the tests. Ideally, I will put these things into functions just to make it a lot easier to read. And so if it's a write test, then I will do this part. If it's a read test, I will do this part. And if it's a bypass, I will do this part. And I can add more and more operations here just to check how it works. Let's just see if this compiles without any errors, which doesn't mean, okay, there you go. This is what I meant. Because I am doing initializations of the same kind of variable in different parts, and this is not a good practice. And this actually throws an error in the compiler. So if I define these as sub-functions, then the definition of variables in the scope of the function will be no problem. If I define different variables with the same name inside different parts of a switch case, then it's going to be a problem. So I think I'm going to do is to cut this into functions instead. So we'll have a function called write test with no parameters. And write test will include this code. This. Then I will define another function called read test. And read test will take the code for reading test. And finally, I will cut away the code for bypass. And we can call this one void bypass. So theoretically, this thing will compile no problem, because then we're defining variables inside the scope of a function, and that should be not be concerning or giving any problems inside the switch case. And there you go, it compiles no problem. So let's see if the bypass test works. So if the bypass test works, I should be able of pushing a sound like this, and a program like this, and theoretically right now I have the bypass program working, which we have no way to see right now that it's working, because it's using nothing that is visible. So as I'm reading and then I'm writing to the DAC, what I could do is to just check at the output whether there is a change when I push data on the input. And in order to do that, I just need to make sure that the write test part can be reused in the bypass part. So I could be reading the signal that is at the output and then print it out on the serial port, and in that way ensure that the thing is working as I expect it to work. Okay, so I will just change this and send this new code. Okay, so right now, if bypass works, I could be affecting the signal at the input, and by affecting the signal at the input, see how it works at the output. So I'm gonna be just putting 5 volts on the input and see what happens on the measurement. Oh, I made another short circuit there, sorry for that. So you have to be careful. The Uno is super robust, so you can make short circuits now and then and things still work. But if you do it in the middle of working, then it's not so much fun. So, okay, now I'm just gonna I'm gonna change the input. And I don't see a clear change here. You see? So the input is 200, 250, 280 of the measurement from the output. And when I just plug in the wire, nothing really happens. So let's just change the volume, which is the signal at the output, to see if we see how this affects. And no, I don't see a clear behavior. I don't see a clear change. So this is the thing that's happening. So the ADC works, the DAC works, and somehow I don't see whether both of them are working together. See, like the values that I'm reading. Oh, wait a second. Wait a second. I'm making something wrong. So I'm actually not having anything connected from the output to A5. So I need another wire. Of course, I'm not reading anything because the pin is hanging loose. So I need to have a cable connected to A5 here on the output directly to be measuring what's going on. And I had nothing. I was changing the input without changing the output. And I made yet again another short circuit, so I need to close the terminal window again and open it again. So this is a common thing. You have to be careful. Again, if you had a different board that wasn't the Uno, this would not be, it would be not so graceful, and it will not break in this very nice way. So you see now by default the reading is 400 something, and when I now trigger the 5 volts, it is a noticeable change, or not. And if instead of putting 5 volts I put 0 volts, what happens? So I don't see, so 460 is the measurement right now at the output. If I put 5 volts, it goes up for a second. If I put 5 volts, so I'm not really clear what's going on here. Because sometimes it seems to be working, sometimes it doesn't seem to be working, and the reason for it isn't clear to me at this point. So I might have to go back and check my assumptions, check cables, check everything to see what might be not working. You see by default there is 460, and when I plug 5 volts, there is not a clear change. Since I'm reading the analog pin, the maximum value I can get is 1023. I'm getting 460, which is on its way to be half the maximum value. So the reading is consistent with having a 0 voltage at the input, but I'm not having a 0 voltage at the input. I'm pushing 5 volts at the input. So I should read a pretty high increase on the input value, which I'm not. Okay. So basically, I need to figure out what is going on, but I haven't a relevant, I haven't a personal issue I need to solve. So I'm gonna leave you for 1 minute, and I'll be back.